Okay, so now in question 1625, what we've got here is a question which asks us to come up with a mathematical description of a wave which is travelling in the negative x direction. So we've been given the amplitude of this wave, its period and its speed, and we're asked to come up with a mathematical description of it. Now, when we're back in here, however many weeks ago, we came up with a mathematical description of a wave that's travelling in the positive x direction. So because that was just so much fun, what I'd like to do here is just to go back and repeat what we did before, but to consider a wave travelling in the negative x direction instead. So let's just go back and have a look at what we did. What we started with last time was we started by considering what the wave looks like at some initial time. So we picked some starting time and we took a picture, or rather we imagined having taken a picture of the wave at this initial time, and we got a mathematical description of it then. And from that we sort of built on it to get a mathematical description of a travelling wave. So here I have a set of axes, and let's just draw up what we expect this wave, what we want this wave to look like at some initial time. So this initial time, which I shall call t is equal to 0, let's suppose that the wave looks something like this. So we're going to have a sine wave, and it's going to go something like that. And so where this is going to be one wavelength along here, and this point up here is the amplitude of the wave, and down here we have minus that same number. Now, when we were here before, we did come up with a mathematical description of it, and that mathematical description was that y of x is equal to the amplitude multiplied by the sine of kx, where the k is the wave number, and that's given by 2 pi divided by lambda. So 2 pi divided by the wavelength. So what this formula does for us is that if we want to know what the magnitude of the wave is at any point along this x-axis, all we have to do is pick that x position and then just take that number, plug it into this formula, and it will tell us what the magnitude of the wave is at that particular point. But now, this is what it looks like at some initial time. So this is what it's looking like at t is equal to 0 seconds. If this wave is actually moving in the negative x direction, then if we wait a certain amount of time and then take another picture, the wave is going to be picked up essentially and moved in the negative x direction. So if we just wait a length of time t, which I'll call t seconds, then after that t seconds, depending upon how long we wait before taking this next picture, the wave might look something like this. So it might be doing something like this. So what I shall attempt to draw here is something which has exactly the same shape as what the wave did at t is equal to 0, but just shifted by a certain distance along the x-axis. And I shall call the distance which the wave has moved d. So I'll call this d. So the wave here has exactly the same shape, it's just being picked up and moved along by distance d. Or rather, it is just moved by distance d. So no one actually did pick anything up. What we now want to do is to get a mathematical description of this one. So essentially what we want is a formula that would allow us to do something like this, to say, I pick this x point here, I want a formula that I could just plug the number that I chose for x into. So I want a formula that I could plug any number of any x into, and that would give me what the magnitude of the wave was at that particular point. What we can do to figure out such an equation is to build on this one here. Because we know that this curve here has the same shape, but is just displaced by a distance d in this direction, we know then that if we pick this point here, say, and we go up to this height here, then if we go back across to the wave at t is equal to 0 seconds, then we're going to come to a certain point at which this wave at t is equal to 0 seconds has the same magnitude. We then know that this distance along here is just going to be d, the distance by which the wave moved. So really, if we want to know what the magnitude of the shifted wave is at this x position, all we need to do is to take that x value, add d to it, and then plug that number into the formula for the wave at t is equal to 0. So that tells us that a mathematical description of this shifted wave then is just going to be this one here, but with a shifted x. So this curve here is going to be, let's call it y, x of t is equal to the amplitude times sine times k x plus d. Now we could ask, what is this d? Well, what this distance is, it depends first of all on the speed of the wave, but it also depends on how long we waited between taking the picture at the initial time and taking the picture after the wave had moved. So if we just call this t, so I've said that this picture here is at t is equal to 0, this is equal to some time t later, and I haven't specified what that is, so I've just left that as a variable. But if we say, let the speed of the wave be v, then the distance that the wave travels is just going to be equal to that speed times time. So this just comes from the speed is equal to distance over time formula, but just rearranged slightly. So if we just take this and plug it into here, what we get for the formula of the travelling wave is this one. And if we now just expand out these brackets, what we find is that this is equal to kx plus k times v times t. And that's the formula for our travelling wave. So last time, in fact, we called this thing here omega, or the angular frequency, and that was equal to 2 pi times the frequency of the wave, but now we've just written it in a slightly different form. So this is in fact just equal to that omega from last time as well. So this equation here is in fact just exactly the same as the equation we had for the wave travelling in the positive x direction. The only difference is this sign here. Previously we had a minus sign there, now we've got a plus. So this thing here is exactly the same as omega, which is 2 pi times the frequency, which is equal to 2 pi divided by the period. So to answer the question 1625, all we need to do is calculate a number for this wave number and a number for this angular frequency, which is equal to the wave number times the speed. So let's just write down what we've got. Well, we know that the amplitude of the wave is 0.37 meters. We know that the period is 0.77 seconds. And we know that the speed is 12 meters per second. So I'd say the first thing we should calculate probably is this wave number, which requires that we know what the wavelength is. And we haven't been actually given that. But let's just remember that in one period, a travelling wave will move one wavelength. So the speed of a travelling wave is just going to be equal to the wavelength divided by the period, in fact exactly what we have over here, And since we're given this and that, we can quite easily rearrange this and figure out what the wavelength has to be. It's going to be the speed times the period. And once we know that, we then know that the wave number is going to be 2 pi divided by the wavelength, which is just 2 pi divided by the speed multiplied by the time. And then that means that k, the wave number times the speed, or this angular frequency, that's just going to be equal to 2 pi divided by the period, which is what we would tend to expect. So anyway, this wave number then, let's put the numbers into the calculator, we're going to have 2 times pi, and that's divided by the speed, which is 12 meters per second, times the period, which is 0.77, and I get that that's 0.680. So it's going to be 0.680, and that is in inverse meters. And I know it's going to be in inverse meters because it's 2 pi divided by the wavelength, and the wavelength is in meters. For the angular frequency then, we just get that that's 2 times pi divided by the period, which is 0.77, which gives me 8.16 per second. So seconds to the negative 1. So finally, just plugging these numbers into here, we get that the mathematical description of the travelling wave is going to be 0.37 sine 0.680 times x plus 8.16 times t.